All right, where did I put that? Good grief. I can't find anything in here. I don't know. Oh, crap. So in this video, we're going to solve Kepler's equation. Kepler's equation is m is equal to capital E minus little e times sine of capital E. Capital M is the mean anomaly. Capital E is the eccentric anomaly. And little e is the eccentricity. Okay, so we take this and we want to solve for e, and so we naively start out with e is equal to m plus little e times sine of e, but then, okay, we have our e is still stuck on that other side. But this actually turns out to work nicely for us because we can do something called fixed point iteration. In a fixed point iteration, you have a function of, say, a variable x, and you have an equation of the form x is equal to f times x. And so you set up a sequence of points, x sub n plus 1 is equal to f of x sub n. And you start out with some x naught, that is your seed value, an approximation of the value you're looking for, and then you continually run through xn plus 1 is equal to f of xn over and over and over until the xn plus 1 minus the xn is within some tolerance value. Okay, and that will be an answer. I've written up this worksheet in Colab notebooks, which sets us up to solve Kepler's equation. Kepler's equation is actually a family of equations which you can put different values of E and different values of M in. I've set this up. Kepler here is actually in the place that this E is, or I guess it stands for what's going on over here. And then I have a program set up here to run it through fixed point iteration. If you want to try this yourself, you can pause right now and type this, okay? And so I've got my fixed point iteration set up to where it'll either go through 100 times or it'll stop if it gets our 16 decimal places of tolerance. And so I do run through it, and this is the answer I get. I actually at this point really don't have any idea how accurate this is, and so for this I'm going to use another method called Newton's method. Okay, so Newton's method is a way to solve equations where we have some y equals f of x, and we find the place where f of x is equal to 0. And the idea is that you pick an approximate to your function, and then you draw a line tangent to your function there. Okay, have the equation of a tangent line, and then figure out where that intersects, and the idea is that that will be closer to the solution than your original approximation. And the formula for that is given by this guy right here. And so we in Kepler's equation, since it is equal to m is equal to E minus E sine of E. Okay, we put this in a form that's equal to 0. All right. And so we set this up to our to be our function as we have here, and then go through our iteration until we have something that converges. Newton's method is just a little bit more complicated than fixed point iteration because we have to calculate the derivative, but it doesn't turn out to be all that difficult in this case. And so what I do here, I define my function, the Kepler Newton function, and this is the derivative of the Kepler Newton function, and then I put it in Newton's method, which will have two parameters. It'll have E and M be the parameters, and then I have lines where I put the function in and the derivative in, and then I go through iterating, and again I am going to put it through a loop a maximum number of times, and so of 100. And so in doing this, I'm going to use my mean anomaly. Okay, is going to be m. I'll put in 0.4 as I did in the case before, and the same eccentricity as in the case before, and I run through it, and not defined. Well, that's because I had not pressed this to define it, and so here we go. Let's do it all again, and there we have it. And so here again we have the same answer as we did before, and so I'm thinking that these are both correct to within 16 decimals of accuracy. All right, where did I put that? Good grief. I can't find anything in here. I don't know. Oh, crap.